Hi everyone, my name's Cathy Wu and I'm an assistant professor at MIT. Over the last few years, we've been doing a lot of work around how to analyze the potential impact of automated vehicles on transportation systems for the coming decades, focusing on computational challenges of these problems and how recent advances in deep reinforcement learning and transfer learning have the potential to help us overcome these challenges. I'm excited to share with you what we've learned so far. As technologists and frankly, as human beings, we have this tendency to see a prototype self-driving car, say from Waymo, and imagine a future of getting back all the time we've spent stuck in traffic, and instead we can relax with our friends. Or imagine highly efficient highways, highly efficient supply chains with automated trucking. Similarly, we might see a consumer drone here from Skydio, and imagine a future where these devices can deliver our packages on demand within 30 minutes, or even bring us to our destinations, leapfrogging over traffic congestion on the ground. We can even get some numbers to back up our excitement. By year 2050, with full adoption of self-driving cars, we could dramatically reduce the number of traffic accidents, traffic congestion, greenhouse gas emissions. We could even grant access to mobility for an additional third of the population, including the disabled, the youth, and the elderly. But if we take a closer look, here focusing on energy consumption in the US, we start to see a different picture. Today, US energy consumption is 31% consumed by transportation. An analysis of full adoption of self-driving cars conducted by WADUD in 2016 unfortunately gives us a high degree of uncertainty, anywhere from a pleasant decrease of 40% to a horrifying doubling of energy consumption. So a lot of factors contribute to this change, including more efficient driving techniques such as vehicle platooning and a set of strategies known as eco-driving. The biggest culprit and uncertainty lies in what's called travel cost reduction. This is where the reduced cost of transport induces new demand that did not exist before, leading to additional usage of the system and thus more energy consumption. This range of -40 to +100% is a result of different weighted likelihoods of these different factors. In order to help us navigate towards the good outcome, we need to better understand this space in the middle. This is the regime of mixed autonomy, where parts of the system are automated and parts are not. We would like to understand this transition from no autonomy to full autonomy, and whether it is to be linear, nonlinear, or has some critical points. Interestingly, from a technical standpoint, we actually also see a similar gap between analyzing individual vehicles and analyzing the whole system. We as engineers have a wealth of tools from control theory, optimization, and machine learning to rigorously analyze a single automated vehicle system. This is what I will call individual autonomy. It's not independent of the rest of the system, but we don't analyze the other parts. This is your single self-driving car, and the goal is to get to the destination quickly, maintain stability, and to not crash into things. We have a $1 trillion industry working on this, and we are making progress every year. But again, we don't think too much about the other vehicles or the infrastructure, so long as we don't crash into them, in part because they're too complicated to include. On the other hand, we have what we might call full autonomy. This is where all parts of the system are automated, all vehicles, the intersections, etc. We also have many techniques to analyze and optimize these systems to determine exactly how many vehicles we will need, how they should all be routed, and how they can perfectly weave through intersections without stopping. The key is that when all parts of the system are automated, there's a lot less uncertainty, so we can analyze many more parts of the full system. However, we run into trouble when we start to look at scenarios in between, when parts of the system are automated and parts are not. Here, we unfortunately have relatively limited techniques, and the difficulties come from many different possible sources of uncertainty, such as from partial observations, from occlusions, or from incomplete sensor coverage of the system, model misspecification from human behavior or of other vehicle dynamics, limited communication with non-automated entities, as well as data collection challenges in large-scale and real-world domains. However, this is exactly the kind of setting that we need to be able to analyze in order to better understand the impact of autonomy as it is gradually introduced. So we decided to pursue the question of whether emerging techniques from deep reinforcement learning can aid in the analysis of mixed autonomy settings. Here, we focus our study on the impact of traffic of automating a fraction of vehicles. Mixed autonomy can take on different forms, so let me give a few examples. Rather than looking at the fraction of automated vehicles, a different kind of mixed autonomy could be within vehicles, a mixed control of a vehicle by a human and an advanced driver assistance system. What would the impact of this kind of mixed autonomy be on the safety, reliability, efficiency, fairness of the broader traffic system? We can take a look at other types of systems as well, across energy, information, finance, and criminal justice. Suppose we were to introduce a fraction of distributed energy sources, for example, electric vehicles, social media bots, trading bots, or automated recidivism scores. What would their impact look like on the safety, reliability, efficiency, fairness of the broader societal system? These systems and questions will not be the focus of this talk, but they all require more analysis tools, and we would ultimately like to see a common methodology across these different domains. So let's cast our problem into the framework of reinforcement learning by considering the agent to be the fraction of vehicles that are automated, and considering the environment to be everything else, including the human drivers and the infrastructure. The agents will make decisions such as when to accelerate or change lanes according to a policy denoted pi in order to maximize reward. We are concerned with global rewards, such as the average velocity for all vehicles in the system. And in the future, we can consider trading this off with energy consumption, travel time, safety, comfort, and other measures. In our work, we will use policy gradient methods, in particular TRPO and PPO, to solve the problem. The goal is to find a good theta which parameterizes the policy such that the expected cumulative reward is maximized. Following the milestone results that demonstrate the potential of deep RL in the domains of video games, board games, and locomotion, we would like to take a step towards societal systems. Ultimately, we will be interested in studying large urban networks where a fraction of vehicles are automated. Unfortunately, these problems are not tractable with the methods that we have today. We will work towards this, but the good news is that we do not need to study the full system immediately in order to start gaining insights into mixed autonomy. So what we do, in our earlier work, we showed what is achievable when training from scratch in small scale environments using reinforcement learning methods and with modest compute. What we've done is design a representative set of scenarios that exhibit a variety of different traffic phenomenon, here including traffic jams, lane changing, merging, intersections, highway bottlenecks, and so on. By using reinforcement learning to learn policies for 5 to 10% of vehicles in the system, we see a 30 to 140% improvement of average velocity across the scenarios. And this does have near-term implications for automated vehicles. In the course of our study, we found that some of the learned policies actually do match the performance and behavior of control strategies devised by experts over the years. Other learned strategies exceeded previous control strategies and do achieve near optimal performance when eliminating traffic jams. These findings provide validation of the methodology in the first place of employing reinforcement learning to analyze the impact of autonomy in urban systems. Here's one finding from our experiments that I especially liked, which is a basic model for studying an intersection. To provide a point of reference, here is a closed intersection network with 14 human vehicle models. There is a clear bottleneck in this network as vehicles obey right-of-way dynamics at the intersection. Now what we do is we swap out one of the 14 vehicles for an automated one, colored in red. And the controller is learned using TRPO. It observes all vehicles and its action is its acceleration. And here's a video of the trained model. The automated vehicle in red actually chooses a particular velocity as to form a train of vehicles behind it that is exactly half the length of the network, and thereby actually completely avoids the intersection. This result is what we might call an emergent platooning behavior between automated and non-automated vehicles, whereas platooning is typically a behavior seen among multiple automated vehicles. This experiment actually showed us that a single vehicle is actually quite powerful, because a single automated vehicle can slow or stop every single vehicle behind it. Swapping out one vehicle for an automated one yielded a 60% improvement in average velocity, and we see further improvement up to 170% when all vehicles are automated. In working our way now up to urban scale systems, we have to first address the simply stated problem that no two cities are the same. It's even possible that no two city blocks are the same. That is, there are a combinatorial number of environments when it comes to traffic networks. So far, we've been training each new environment from scratch, but that's not going to be tractable moving forward. To be more concrete, let's take a closer look at the environment piece of the reinforcement learning loop. In our work, we use an open source traffic microsimulator called Sumo. Traffic microsimulators are actually used to plan cities. These are among a rich class of urban simulators, and they define characteristics that can be used to simulate individual vehicles in a system, which is microscopic in the grand scheme of whole cities. One of the basic behaviors of an individual vehicle is car following, which dictates how vehicles accelerate in response to the distance or relative velocity of the vehicle in front of it. A very popular model which we employ to describe this kind of behavior is called the intelligent driver model, given by this differential equation. And these models are designed to be quite interpretable and calibrated to real driving data. But this is only the most basic of behaviors, and these models need to be supplemented with much more involved driver behaviors, such as fail-safe logic, merging, lane changing, and so on. These behaviors cannot as easily be written down as differential equations. These behaviors in turn must be coupled with important simulation elements, such as road networks, roadway signage, and so on. Although it is quite common in RL research to skip the details on the environment, here I want to point out a striking feature of traffic, which is that the combination of all these different features leads to a combinatorial set of possible environments. And this really motivates our interest in the concept of transfer learning. So we're interested in where knowledge could potentially be transferred across traffic scenarios, and whether this could be a promising direction to help improve the sample efficiency of reinforcement learning on these tasks. We refer to transfer learning from a source task to a target task as the use of knowledge gained to bias the learning process on a target task towards a good set of hypotheses. More specifically, zero-shot transfer is the extreme setting where no learning is done on the target task, and it is analogous to out-of-distribution generalization in supervised learning. So we start by examining scenarios where we intuitively expect transfer to be successful. One of the simplest possible traffic settings is this single lane circular track, and the performance upper and lower bounds on the average velocity can be characterized by computing the system equilibria of the corresponding dynamical system. Here we can see this in the figure for a range of traffic densities in the x-axis. We also give the state-of-the-art controller by Stern et al. In blue, which is a hand-designed proportional integral controller with saturation. And we can see that it performs better in lower traffic situations and worse in higher traffic situations. We now take the white range of densities in the middle and call this our training regime, or our source tasks. We take the gray density ranges on the outside to be our testing regime, or our target tasks. Our learned controller actually achieves near optimal performance across the board. This is perhaps not surprising that some amount of transfer should be possible, since the network and the underlying dynamics are quite similar. What's surprising here is that the zero-shot transfer retains the near optimal performance. One of the common criticisms, however, of the circular track is that it does not have any bearing to reality, since most real traffic systems are open networks. In collaboration with Abudi at Berkeley, this motivated us to assess whether, from a learning process standpoint, there is similarity. That is, whether knowledge can be transferred between closed and open networks. There are a few substantial differences between open and closed networks, which I won't get into here, but the consequence of these differences is that in the open road, in order to have an interesting traffic problem, we need to introduce a merge point to introduce some perturbations into the system. Following that, then we can directly transfer the policy learned in the closed system to the open system. And already this yields an average velocity higher than that of driving performance of humans. The performance can then be fine-tuned from there. This experiment provides evidence that knowledge from closed networks, which is most of our early experiments, can actually be transferred to open networks. Finally, in ongoing work led by Z and my research group, we are studying the potential for a single policy to transfer to many different scenarios. Here we study a traffic bottleneck, which is characteristic of many highway networks. An interesting aspect of traffic bottlenecks is called a capacity drop. If we take a look at a diagram which characterizes the relationship between the inflow of vehicles into the system and the outflow of the system, a capacity drop is characterized at first by a linear relationship, which is what we would expect. And then instead of leveling off at the capacity of the bottleneck, we instead first see a drop and then a leveling off. When we employ RL to learn a policy for 10% of the automated vehicles, we can actually see that we're able to avoid this capacity drop and increase the throughput. And we see this interesting behavior emerge where the automated vehicles take turns holding back strings of human vehicles, which avoids contention at the bottleneck. We now treat this as our single source task. And we find that this policy actually transfers well to different bottlenecks with different numbers of lanes and segments. It also transfers well to different fractions of automated vehicles. Here, for example, we see a graceful degradation of the performance to the capacity drop as we decrease the number of vehicles that are automated. We then take the same policy from the bottleneck and transfer it to what looks like a very different network, and one that we are not currently able to train from scratch. And this is our 3x3 grid network. Taking a look at the intersection highlighted in red, we can actually see behavior from the automated vehicles that is reminiscent of the bottleneck. This result from a zero-shot transfer experiment gives an improvement of 26% in throughput over the human driver baseline without any fine-tuning. Ultimately, we want to have a set of techniques which can help us integrate autonomy into existing systems, such that the outcome is safe, reliable, efficient, fair, and many other desirable objectives. This means rigorously studying mixed autonomy systems. In this talk, we motivated how deep reinforcement learning is a promising technique for this toolkit. Not only can it help inform transportation science in the context of mixed autonomy, but similarities within traffic scenarios can be leveraged for more efficient reinforcement learning. But there is a long road ahead. As we move forward, it will be important to continue to scale reinforcement learning techniques such that they can be used to study richer and urban scale systems. There's also a question of how to turn these scientific insights into actionable decisions to actually improve our urban systems, either through long-term decision support for planners or near-term decisions for automotive manufacturers and self-driving car companies. Along the way, our systems and human behavior will change, so it will be critical to cope with distribution shift or find more scalable ways to model human behavior so that our analysis can match reality. It will be interesting to better understand how different analytical tools can complement one another to address these problems, such as machine learning techniques and model-based techniques from control theory. Finally, I want to take a moment to thank all of my collaborators and partners on this project, including my student Z, collaborators at UC Berkeley, and discussions with too many friends and colleagues to include on this one slide. Thank you.